remember till now, just making a short summary. We have seen some direct methods to study side effects. The first one were mainly based on the usage of earthquake recordings, and we saw the possibility of comparing earthquake recordings collected by a network of stations. Then we also saw some methods working with only one station. So for example, the H/V of earthquake. And then, and we consider also the works of this with spectral ratio working with Boros recording. Then we introduce a little bit the usage of seismic noise. And mainly we focus on the usage of seismic noise on singular station, and in particular on the H/V spectral ratio. So, and we show which kind of information can be retrieved if we use only a station. And we also saw different possible use of H/V in terms of estimating the resonance frequency, in combination with independent information from borers, for example, as a tool to map the geological bedrock. And also we saw the possibility, if we have some other information, to invert the H/V in order to obtain a shear wave velocity profile of the underground. We know that if we know the profile or of the structure of the underground, then we can, in some way, try to calculate the site response through numerical simulation that can be from very simple, in simple 1D, to 2D and 3D, and so on. Okay, these are just some of the tools, and we also, if you remember, introduce shortly a little bit some information about inversion. So how, starting from the inversion, we can, using the inversion and the information that we get from the H/V, we can obtain the shear wave velocity profiles. But we also said this would be the same if instead of having the H/V, we could have a dispersion curve, for example, of surface waves. Can be Rayleigh waves, or can be love waves, or can be even both. Okay, so now we will start looking at some methods that generally use to calculate the dispersion curve, mainly for Rayleigh waves, but not only, and how they can be used, this dispersion curve. So maybe we repeat a little bit the inversion procedure we have seen last time, how we can use this simply to obtain 1D profile of the underground. Of course, I will show this in this course mainly at a small scale. So I mean at the scale of tens of meters or hundreds of meters. But in principle, the similar analysis for surface waves can be done also in standard seismology. If you want to study, for example, the shear wave velocity structure of the crust, or even of part of the upper mantle, so of the lithospheric structure. So in that case, you are changing frequency range, you are using much larger arrays, but in principle, some of the methods are, in a way, very similar. So let's start with the simplest case, which is the case of linear arrays. So linear arrays, it means generally we are talking about tools that are generally used when we can make use of an active source. So we deploy instruments in the ground, general, at a different distance along the line, and then we have something that is sending energy to the ground that is producing, let's say, seismic waves that are recorded at the different instruments. One of the methods that was used a lot in the past, because it was quite simple, and was very much used in the geotechnical community is what is called SASW, so Spectral Analysis of Surface Waves. The method was used a lot in the geotechnical community till a few years ago. So you will find still, maybe at accelerometric or strong motion stations, many of the velocity profiles that are accompanying the data that you can obtain from the database. You will see for these stations maybe velocity profiles that were calculated using this approach. Nowadays, other approaches are more used, but as I said, many of the velocity profiles you will find are still based on this kind of measurement. So it's good to know it. How does the method in principle work? So you see here, you can be here, one of you, just exciting with a hammer the ground, and the method is requiring that at least two geophones, generally only vertical geophones were used, because the analysis was mainly carried out for Rayleigh waves. So two geophones were placed at a certain distance with respect to what we could call a center point. The waves generated by this source were recorded by these geophones, and very often they were not even recorded, but they were automatically analyzed by the instrument to which the geophones were collected. Then the energization was repeated by the other side. Another two recordings were recorded and again analyzed, and the two things were compared. So this was not sufficient in general, since one wanted to analyze a wide spectrum of frequencies. The experiment was repeated, increasing the distance between the geophone and even increasing farther than the distance from the source to the geophone, in order that more low frequency for the low distance was becoming available, and a wider, as I said, spectral range was analyzed. So how the method of analysis was working? So the signal that you have seen arriving at the geophone was transmitted to the analyzer, that was that instrument. The signal were transformed in the frequency domain, calculating the Fourier transform. And from the Fourier transform, the cross power spectrum between the two sensors is calculated. So it means I take the Fourier transform of the signal at geophone 1, and I multiply the spectrum for the Fourier spectrum, or in case the conjugate spectrum of the recording at the other side. So conjugate means that I change the sign of the imaginary part of the spectrum. You remember, each Fourier spectrum is a complex number with a real and an imaginary part describing, let's say, each frequency. To make the cross spectrum, so to correlate the signal, I simply take the Fourier transform of one, the Fourier transform of the second one, and I just change the imaginary part sign of the second one, and I just multiply the two spectrum. What I obtain is a cross power spectrum doing this. And why I do it? Because the phase that I obtain in the cross power spectrum, it's already giving me an information about the phase difference between the two signals recorded at the different stations. And I will have, since it's a Fourier transform, I will have a phase difference for each of the frequency that is in my spectrum directly. Because we know that the phase difference is related to the time delay of each frequency. And we expect that, for example, if we are looking at Rayleigh waves, different frequencies will arrive at different time at the different stations because of the dispersion that we already discussed. So every frequency is propagating with a different velocity. Since it's propagating with a different velocity, every frequency in my signal will arrive at a different time at the two sensors. I can measure this difference in time for each frequency automatically in this way. So looking at the Fourier spectrum of each signal and calculating the cross spectrum, automatically I have a phase difference. So if you imagine that this is the phase of my cross spectrum, so this is the phase difference that I have between the two signals at each frequency, if I want to calculate the travel time from the source, between the two receivers of each frequency, I simply have to divide the phase shift for 2p and the frequency value. I imagine this is quite simple. So the phase will be a number going from, if you remember from a sinusoid, is just a number going from 0 to 2p. No? Is the full circle that we can do. So if I consider a full phase circle, will be 2p. If I just shift the signal of amount theta, this will correspond to a time t. So again, if I have a sinusoid, the full circle is 2p, and this is equivalent to a full period t of the signal, which is inverse of the frequency. So we can write that a full circle 2p divided the period is equal to a small change of phase, delta, indicated here, divided the amount of shift of the signal in time that I have. So immediately you can calculate this equation so that the travel time, the shift of each frequency is equal to the difference of phase divided to PF. Okay, now I have a travel time between the two sensors. I know the distance between the two sensors, and therefore, for each frequency, I can calculate the velocity at which the waves are propagating, simply from the distance divided the travel time. So if I want, I will have for each frequency then probably different velocities. Why we have this, we already showed it a little bit last time. If we consider the wavelength of a signal as calculated from the velocity divided the frequency, and we know that longer wavelengths, so lower frequency, you see here, are deepening, are propagating deeper in the inside part of the Earth, and generally they have a depth of investigation that depends on the wavelength divided 2 or the wavelength divided 3, we can immediately understand why we have this dispersion of Rayleigh waves. So the high frequency, so small wavelengths, they penetrate not too much in the Earth, so they only propagate in the shallow layers that generally have low velocity. The low frequency, they have long wavelengths, they penetrate more inside of the Earth, so they propagate not only in the first layer, but also in the deeper layer. And these deeper layers are faster, and therefore the velocity of this perturbation of this frequency is larger than for the high frequency. Okay? Till now it's all clear? Okay. So this is a very simple method. If you think to it, I just have to go in the ground. I just place my sensor. I just excite waves using, for example, a hammer or vibrators or other tools, and recording and looking at this phase shift, I can immediately calculate my velocity as a function of frequency. That is the dispersion curve. There are some troubles, of course, with this method. Of course, the first point is that in the low frequency range, so if my source is too close to the geophone, I cannot be sure that my vertical component is really strongly dominated by surface waves. So for example, if I am too close to the geophone, still the body waves can be quite strong. So they can make some disturbance to the analysis of phase and therefore generate some mistake in the analysis. The other problem is that there is not a real, let's say, criterion on how to place the geophones in order to have good results and what is the position, for example, of the source. In some cases, for example, it was empirically estimated that we can keep D1 equal to D2. D2 is the distance between the two geophones, can be identical to the distance between the source and the geophone, and this is allowing to obtain wavelengths which are 1/3 or 2 times of this distance. That's why increasing the distance, we are also increasing the wavelength that we can consider. Tokimatsu proposed other criteria. So he said, okay, we can define some intervals of distance depending on the wavelengths that we would like to introduce, or we would like to estimate for the velocity analysis. Other problem is that, okay, it's very nice that we work on the Fourier transform, but all the methods that we will see today, all these methods are mainly based on the estimation, let's say, of a shift between two signals. And you can estimate the shift, for example, from the correlation analysis in the time domain, or like we have seen just now, also from the difference of phase between the two signals after that we transform them in the Fourier domain. Fourier is simple because then if we work in the time domain, we cannot see the phase difference or the time shift of each component or each frequency of a signal. With Fourier, we can, but there is a small problem. The small problem is that the phase difference that I calculate in the way I showed you before, so from between two frequencies, is given you back by any routine, let's say, that you can use, generally in the range between -p and +p. So, or if you translate in degrees, -180 degrees or +180, or depending on the convention that you are using, can be 0 to 2p. So this can be a problem. Just imagine if your signal has a small wavelength, like we have seen in the first lecture. Remember, we showed the equivalence between frequency and wavelength and so on. So if you have a small wavelength signal, but a large distance between the geophones, the signal will propagate from one geophone to the other, making more than one cycle. So the phase difference between the two geophones for that frequency will not be in the range between, let's say, 0 and 2p, but will be bigger than 2p, or several times the number of cycles that has been done. Every cycle is a 2p phase. So it means that in this case, if I do not correct my phase spectrum for accounting that my phase at different frequencies is increasing and it's becoming certain number of cycles more than only this small difference that the routine is giving back to me, I could make very large changes, very large errors in the velocity estimation. So just imagine to have a small signal wavelength, and before reaching the next sensor is making one cycle plus another small part of a cycle. When you will calculate with this method the phase difference, you will get only information about the small part. So if I'm not correcting for the fact that another cycle was done before, what will happen? Okay, I have a signal, a frequency to which I give a small phase difference, but the distance is large. So you see immediately that a small phase difference means for the same frequency also a smaller travel time. But since the velocity is calculating from distance divided travel time, so what will happen? That for a large distance, I will use a small travel time. So I will give to this frequency a very high velocity of propagation, which is wrong. It's simply because I didn't take into account that this frequency before had made some cycle. Generally, this can be done correcting the phase spectrum for all these number of cycles. And this is called phase unwrapping, which is something that is generally done and can have also some problems. So we can unwrap the phase, we can measure the right phase difference and therefore the right travel time, but there is still a but. What is the problem in this case? The problem is that when I use a energetic source, for example, my hammer, I'm having a lot of energy. My spectrum will be rich of frequencies that are generally quite high, maybe 50, 70 hertz. But when I start the unwrapping operation that I was describing before, I start nearly from zero frequency. And the zero frequency can be probably very poor in signal because my original source was not exciting these frequencies. And therefore, I start propagating in the unwrapping of the phase some noise to the higher frequencies. The other reason why maybe I don't have a lot of signal can also be related to the instruments that I'm using. Why this? Because the instruments are always sort of like, they act like a sort of high-pass filter. So for example, if I use 4.5 hertz geophones, I show you already last time, it means that I will start filtering the signal, let's say below 4.5 hertz. I start even a little bit before, and also distorting the frequency. So if my filtering is very strong, what can happen? That at a certain point, the signal can become smaller than the internal noise of a sensor, like we have seen last time. And if this is happening, I have no information anymore on the real signal that I excited. So when I start making from the zero frequency the unwrapping of a phase, I will only propagate only noise in the good, let's say in this way, frequencies. So this could be also another limitation that we can have with these methods when they require this kind of approach. So we also try to solve a little bit this problem with some other methods. For example, we propose an alternative method that was also allowing to study very local structure, but in which the analysis was not based only on providing one single value of two recordings, but making some analysis on the whole filtered record of each one of the two geophones. So in principle, the method was based on making a filter for each frequency we wanted to study of the recorded seismogram. Then we calculate what is called compressed trace. So you just combine in one trace the real and the sort of imaginary part of the seismogram. So with this method that is based on the Hilbert transform, it's possible again to obtain the dispersion curve, also with methods similar to SASW, but with some statistical analysis of the dispersion curve. More used, and you will find much more literature on this, is the use of multi-channel analysis of surface waves. So nowadays, with respect to the previous methods, it's possible to have instruments with many channels that therefore can record the motion with many instruments in different positions along a line. So again, these methods are working in placing in a line different geophones, not only two, but you can reach a number that depends on the capability that your instrument has. And by one side, at a certain distance from the geophones that has been deployed on the ground, one can start generating seismic waves. For example, the typical sledgehammer. Waves are generated, and of course, in your wave field, you will have some body waves, which are becoming smaller and smaller with distance, and you will have a clear predominance of surface waves. This is a typical kind of recordings where in the y-axis you have time, and on the x-axis you have every recording in each position of every geophone. What you can observe quite clearly is that you will have different arrivals with different amplitude and frequency as a function of time, and you can immediately identify here in this part the surface waves where they have also a clear dispersive behavior. See lower arrival, lower frequency arrival first, and then higher frequency arriving later. How is the analysis to estimate the dispersion curve carried out? Well, again, we play on the phase shift. So the trick in a sense is I have recordings like this. They arrive later and later with distance because, of course, more far away is my sensor, longer will take for the waves to reach the sensor. So if I would know at which velocity these waves are arriving, I could correct, let's see, this slope that depends on the velocity of propagation in order to align along the correct slope all the seismogram, and I could stack them, let's say, in order to obtain the maximum. But I would like to do this for each frequency of the signal, not for the whole seismogram, because different frequencies can propagate at different velocity. So how to do it? Again, we do it making use of a Fourier transform and measuring in some way the phase difference between the recording, so between each frequency in each one of the recording of every geophone. So what I do, I take my data, this is A, is nothing else but just imagine for each position X, I put the Fourier transform of my signal that I recorded. So in the first position of the first sensor, I will have a Fourier transform of the first recording. In the second position, so it can be a second column in a sort of matrix, I will have a Fourier transform of a second recording. In the third position, the Fourier transform of a third recording, and so on. And now, how to find the best, the velocity at which each frequency is propagating? Okay, I can just tentatively shift with a tentative velocity. For example, here you see V, each frequency. So if I change this term, you see is changing the phase. Do you remember this? We saw it in the first equation. This term is just like multiplying for a cos term and for a sinus term our Fourier transform. So it means I'm not modifying the amplitude, I'm simply shifting this observed Fourier transform and simply modifying its phase through the multiplication with this term. And the phase shift depends, of course, on the distance at which every sensor is found and a tentative velocity that I assign to each frequency. If the velocity will be the correct one, this summation will be the maximum because I am stacking in the correct way. If the velocity is the wrong one, this summation will not have a maximum. So I look for many velocity V, to which is the velocity that for each frequency is providing the maximum of this summation. It's an integral, it's a summation in discrete form. So let's try to see a little bit again how it's working, making a simple example. This is just a simplification, but maybe to explain you a little bit better how it's working. So I have a Fourier transform of my signal, which is this, which is complex. You remember, this is the amplitude of a Fourier transform, and this is just the phase component. What I'm doing, I take my spectra and I try to shift them to modify its phase until the recordings are all aligned and I can stack better. So if you think this into the time domain for a single sinusoid, so in the time domain, we said if the distance is increasing from the source, x1 is the nearby point, x2 is a middle point, and x3 is the most far away point, my wave will arrive at different time in the, and later, let's say, in the most far away point. The slope that you see here, that is describing the arrival time that is increasing with distance, depends on the velocity, because it's distance, you see, time. So you can see that the slope of this line is 1 divided v, so it's depending on what we call the slowness parameter. But so it's in a way depending on the velocity at which the waves are propagating, okay? So, and here, as I mentioned, if I want to modify the phase, if I assume that the original phase of the signal was 0, I can calculate a new phase shift simply from 2pf, so omega, divided v and multiplied x, which is exactly, if you think, the equation that we have seen here, that is relating the travel time, you see, it's the equation that is relating the travel time to the phase. So if I multiply, this is omega for t, I will obtain the phase difference. So I'm shifting the signal. I'm always playing with phase and time. And you know, t, we know, is a velocity, is a distance divided velocity. So you see, this is exactly the same equation. So I'm just modifying, modifying the spectrum, the phase of a spectrum with this term that you see also here. I'm just trying to change, to adjust the time here at which the signal is arriving. Okay? If I will be able to adjust it in this way, okay, when I make the summation of a seismogram, think now in the time domain, I will have a maximum of my function, which is equivalent to have a maximum of my function in frequency. So I'm looking for this, but I don't know the value of velocity. So I have to test many of these values until I found the maximum. As I said, when I multiply my spectrum for a term like this, I'm just multiplying two complex numbers. One is the one describing the spectrum for one which is relating or determining the phase shift. And you see this part is not modifying the amplitude of a signal because it's just a simple sinus plus cosinus square. So this will have a modulus equal to 1, but this is adding a phase difference equal to this term, to my original signal. Okay, so I can just select a velocity. I modify all my spectra, I stack them, I sum them, and I will obtain for a tentative velocity v, for each frequency, a value of this summation. Then I can change velocity until I find the maximum of this function. So what's happened? If the velocity that I'm using is too small to correct, no? What is happening? Okay, it's too small. The travel time will be very large. So x3 is too much, it's corrected too much. So for absurd, I will have a seismogram, waves that are arriving first at the most far away site, then at the nearby site. So what will happen? Okay, if I now stack these results, for sure, I will not have a maximum. You see, I can stack a maximum with a minimum, maximum, minimum. So this will be nearly equal to 0. So it will not work. If I would choose a velocity that is too large, then my travel time correction, same distance, large velocity, the travel time will become small. So I will correct, you see, I will correct from the black line to the red line. So I will adjust a bit my seismograms. But what is happening? Again, yeah, it's getting better, but still I do not align with this peak. So when I make a summation and again, mixing things. So this term will not have for sure a maximum. But if I find the right velocity, then I will be for each frequency in the condition when I'm only stacking coherent information, a maximum with a maximum, a minimum with a minimum, and so on. So this function will have a maximum. So as you see here, this is a function of the frequency and of the velocity. So if we obtain this, you can imagine you will have in each maximum a value, which is the maximum for each velocity corresponding to a certain frequency. So automatically, picking the maxima on this function, you will get an estimation of a dispersion curve. You can do this if you remember the properties of a Fourier transform. We said that the Fourier transform of a sum of some signal is equal to the sum of the Fourier transform of each signal. So we can, in this case, we were first calculating the Fourier transform and then shifting and then summing. But of course, we can also first change the time arrival of a signal in the time domain and later, so calculate their summation and then calculate the Fourier transform. So the two things are equivalent, okay? So we can first calculate the Fourier transform, shift them and sum, or we can first shift the time domain signal, sum, and calculate the Fourier transform. And that's exactly what I will show here. So differently from the case before, this is another example of recording where you have body waves and you have surface waves, very clear, you see very large amplitude. You can also clearly see the dispersion, low frequency, and then the high frequency arriving later and with smaller amplitude. How we can then make this transformation working more in the time domain? This is what is called length stack. So we will take our signals, which are functions of distance and time. We will first correct them in the time domain for different slowness, and only later, so slowness, therefore velocity, and only later we will calculate the Fourier transform. So we do it in the other way around. So how we can do this? This is just, again, a series of many seismograms observed at different distance from the source. Let's say the first one, where you have the first arrival, is here, and then the most far away is indicated as 60 meters here, is the one that you see to the right. The first thing that we can do, so we know that we have many seismograms that are function of x and function of the time. Now what I can do, I want to correct this seismogram, I want to align them a little bit. So I just select a certain slope of the line, which is our slowness that we have seen is 1 divided velocity. So I'm testing a velocity. And what I do, okay, I start from the first sample here, and I sum all the points in the next seismograms that are lying on the red line. I just sum all of them. So from all these, let's say 60 points, because it's 1, 2, 3, 4, 5, I get only 1 point, which is just the summation of all of them. Then I go to the next sample just below here, and I repeat the summation. So it's like summing all the seismograms, but for different samples. And the number of samples depend on the slope related to this velocity. So for each one of these slope, I will have a new seismogram, which is the summation of all the seismograms along this line. Okay? So I start with the first sample. I sum all the 60 points here. and I have a first point of a new seismogram, which is a summation. Then with the same slope, I go to the next point and I make the summation. Then I go to the three points, point number 3, and so on, for one slope. So for one slope, I have one new seismogram, which is the summation along these red lines. Then what I can do? I change the slope. So I test a new velocity, and I will get a second seismogram for a second slope. And so on. I can do it for as many slopes, so as many velocities I want to test. Then I will have a new matrix in which I have, for each slope, a new seismogram as a function of time. For each one of these recording, I can make now my Fourier transformation. So immediately I will have a sort of new matrix in which each column will be the Fourier transform of each seismogram for each slope. So will be a Fourier transform showing a value of frequency. So the amplitude for each value of frequency that I choose and for each value of velocity. So again, if where this value will have a maximum, it means that I was summing the seismogram for the correct slope. So in both cases that we have seen till now, you will have something like this, where you have the slowness, or I plotted here directly the velocity, which is 1 divided the slowness, as a function of frequency. You see that you can clearly see some maxima in this function, that is function of frequency and velocity. And we can pick then the maxima. So these highest value are corresponding to the maxima of a function S that depends on frequency and slowness. So these maxima are telling us that if I correct frequency 10 Hertz for 600 meters per second, I will have my signal, my sinusoid at 10 Hertz that are best aligned. So I found the velocity that is better approximating the velocity of propagation of 10 Hertz through my array. You immediately see that the velocity is not the same for the different frequencies. So we have a velocity that depends on frequency, and this is due to the dispersion. And it's also telling us, for example, that the velocity is increasing with depth. We see it here because, for example, at 10 Hertz, we have 600 meters per second. So we said that the depth of investigation is nearly the wavelength divided 2. So if I just make a rough calculation, 600 meters divided 10, 60 meters divided 2. So with this analysis, I can investigate down to 30 meters. If I look in the high frequency range, we are around 200 meters per second, let's say 40 Hertz. So it means 200 divided 40 is 5. If I divide it to 2.5 meters. So with this dispersion curve that is indicated here, I have information as average in the uppermost 2.5 meters, and I can investigate down to 30 meters depth. Okay? Is it clear how it's working? And with the phase and time domain?
Yes, but I have a question.
Yes.
What about if I have an inversion in the velocity profile?
You will have very likely a large amount of higher modes that are generated. So this is mainly the fundamental mode. Velocity inversions. Wait. You are too fast, Chiara. Wait.
Maybe.
I'm coming. Wait. That is no, wait. Can you still see the screen?
Sì.
Okay. Give me only 1 second. Find it. Perché non trovo? Non trovo per gli HSV. Okay. You can see it here. No, we short discussed it last time. If you have velocity inversion, like for example, in the, just imagine, for example, case 2, which is here, you see?
Mm-hmm.
Okay. Generally, when you are using active sources, it's quite easy to distinguish the different modes of propagation. So what can happen with inversion like here, sometimes the dispersion curve that you are observing is neither belonging only to the fundamental mode nor to the higher modes. So it's like if you have different modes arriving very close together, no, with similar energy, and you cannot distinguish them. So the dispersion curve that you obtain is what is defined as a sort of apparent dispersion curve. The same you have it here. You see, you have quite significant inversion of velocity. So you have a first layer with 80 meters per second, for example, an increase of velocity 180, and then a decrease at 120, a sort of sandwich, because then the velocity is again increasing at 360, right?
Mm.
In this case, what is happening, you see, you have quite a strong modes. So you have a jump of modes in this frequency range, where you go from the fundamental to the second or even to the third mode. And in between, you have something which is not exactly belonging to mode number 1 and mode number 2, let's say. It's a sort of apparent modes. In other cases, you can see this better, but this is really a typical example where this is happening. Another thing that we observe is when you have thin layers, superficial thin layers, and a stiff bedrock just below it. I remember we had this problem in some stations in Liguria, for example, some in the characterization of some of these stations. What can happen is something that you see a little bit here. So can happen that also in the low frequency part, what is dominating is not anymore the fundamental mode, but is the first mode. So you can have a mixture of mode, and this can be strongly misleading. So the first mode is becoming dominant, also where you generally would expect the fundamental mode to be more important. So in good cases, let's say of active source, you can distinguish the modes very clearly. When you have inversion of velocities, the modes can play this game, let's say. They can give you some apparent dispersion curve. And this can be a little bit tricky if you don't deal it correctly. So for example, if you try here in the inversion, if you make an inversion forcing the inversion to generate only a dispersion curve based on the fundamental mode, in order that the fundamental mode is fitting your observed dispersion curve, which is apparent, then you will generate a strong artifact and large velocity variation in the model. So you will see very often models with very strong increase of velocity, which is justified only by the fact that you try to fit at all the cost with this mode, the fundamental one, the apparent one. And this is generating some very large artifacts. And we had a very large experience of this problem in the past, unfortunately. This was happening very often. Is it clear, this, Chiara?
Yeah. Grazie.
So one has to pay a lot of attention in this analysis, and that's why, for example, very often we let the inversion to decide in a way if the dispersion curve is apparent or is dominated by a fundamental and higher modes. So in principle, you can imagine, like in the genetic algorithm inversion, you can generate many models, and this model generate a dispersion curve that can be only pure fundamental mode or apparent and so on. And the inversion is deciding in a way which model is best fitting the data, so without generating too large artifacts. Okay? Did I answer to you? It's clear?
Yeah.
Okay.
Thank you.
But this is really an important issue, because otherwise, especially until the studies of 2005, many studies done in the past, or before these dates and before the problem became, especially also for the applied, let's say, seismological community or geotechnical engineering community, this was not so much considered, this problem. Most of the inversion were done in a very simplified way, always considering the predominance of the fundamental mode in the dispersion curve, that you can more or less see here, which is okay. But this was then generating, in some cases, very, very large artifacts in the soil velocity profiles. This could be really, should be considered very carefully. Okay, if you don't want to use, or let's put it in the other way around, the same methods that I described you till now with MASW, either that you work with a Slane stack or with a tau P transformation, so it doesn't make a large difference. But the same method was then applied also to linear arrays with usage of seismic noise. No? So instead of using a hammer or whatever active source, it was said, okay, I just deploy on the ground my sensors, I acquired seismic noise, and I perform exactly the same analysis. Okay, this method is called REMI, so refraction microtremor. I think you will find some studies, and was mainly developed in the University of Nevada, so by John Louis. In reality, as I said, it's doing nothing else but what you do with in active source. But there is a problem that anyway, you are using high frequency geophones. So you don't have really the big advantage that we generally expect from the array of noise that is related to the fact that noise has more low frequency component than the active source. And therefore with noise, generally speaking, we can go deeper, let's say, than with the active source. You are using the same geophone, so there is not this large advantage. Generally, the quality of the results, since you don't have an active source, of course, is not as good as what you have with an active source that you can control and you put directly online with the instruments. And honestly speaking, using a sledgehammer in the ground, it's quite easy when you're there. You can even decide to jump. It's always a signal that you are inducing. So in general, this method, since the source is not in line with the geophones, may suffer from some let's say, homogeneous distribution of a noise source that can bias the results of your velocity analysis. So generally, I would say that nowadays we are not so keen to suggest to use seismic noise in this way. So we really like the use of seismic noise, mainly for larger array. But as I said, if you already have deployed instruments in the ground, it's so easy at that point to just generate a signal that is propagating through the array. But I don't really see the advantage of not doing it, considering that if you don't do it, the quality of the results will be for sure lower. So in general, also in this Cosmos committee, which I belong, where we are reviewing, let's say, the non-invasive method for studying the shallow underground structure, we are not so, let's say, convinced that this could be a good solution. Of course, you can use it, but my suggestion would say, okay, if you have already the instruments on the ground, just try for this shallow profile to have also an active source, and very likely the results will be better. So I don't really see why to do it. Okay, this is for the linear and mainly for the active source arrays. And we have seen that these methods are working very fine because you have a source, you know where the signal is coming from, you can immediately measure the travel time and the phase difference in one direction. And in this way, you can obtain the dispersion curve, and then later you can invert it. But as I mentioned, one of the possible limitations is that with active source, generally we are looking at high frequency. And this means we can have some limitation on the depth of investigation. So high frequency, low, I want to remember, high frequency, small wavelengths, small depth of investigation. But if I'm in an area where I have several tens of meters of sediments, or even hundreds of meters, and I would like to study the underground structure more, I need to have a chance to have low frequency signal that can be very difficult to generate with active sources, and especially in urban areas. So seismic noise is offering the chance to investigate also deep sedimentary cover using these other methods. In this case, the arrays are not linear anymore, but are just, let's say, 2D arrays. So it means we are placing the instrument in different position on the ground in 2D, and we want to study on how the waves are propagating under the array. We try to extract the velocity for each frequency, so the dispersion curve. Of course, what is the condition that we impose, the assumption that we are making? The assumption is simply that below the array, the structure is mainly 1D. So there is no significant lateral velocity, lateral heterogenesis, lateral change of velocity below the array. So the method is not really new in the sense that, let's say, the most cited paper discussing this method is probably the Aki 57. So Katie Aki, a very famous, or probably the most famous seismologist, proposed this method at the end of his PhD thesis. And probably he was not even the first one proposing him. A couple of his colleagues in Japan before him already introduced the method. He had a big merit, especially to make it, especially for that time, a little bit feasible to be applied by the computational point of view. In reality, the method introduced in 57 was still quite complicated to be applied for the instruments required for the calculation, and it had to wait over nearly 30 years before it could be used again, let's say in middle of the 80s when computers developed a little bit more. You have to imagine that calculating a cross correlation or a Fourier transform at that time was very, very, was not easy, let's say. It was a very cumbersome task. So he proposed the idea of Aki, if you read the paper in 1957, which is, in my opinion, a very nice paper to be read, is he was just introducing the analysis of seismic noise as a tool for investigating the shear wave velocity structure below a site. And of course, if you know the shear wave velocity structure, you can then calculate the response using numerical simulation. So what has done? He had derived dispersion curve, looking again at the correlation between the noise recordings, which are made at sites which are close to each other. So like we have seen before, again, he was using a sort of correlation of signals. We will see that the difference, the main difference is not, was that due to limitation, of course, in the calculation. He couldn't look at for each frequency at the phase shift, but he was looking more at how much the amplitude, let's say, the correlation for each frequency was changing with distance. Of course, the correlation of two signals is changing with distance because they are more and more out of phase. No? If I take two signals which are more and more far away, they will be more shifted in time, right? So the phase difference will be larger. And of course, if I correlate them, no, their similarity is changing, it's becoming smaller and smaller, more I go far away, okay? So the concept is always how much the phase is playing a role. Before we were saying, okay, we use this information to directly calculate the travel time at which this wave is propagating. In this case, we look more on the effect of the phase shift on the similarity between, let's say, the two signals at the zero lag. So how much of this similarity in the correlation is changing. But the concept was already there. So he was assuming that seismic noise is made mainly of many waves that are propagating in the horizontal plane, coming from different directions and with different powers, random. But all these waves with different power coming from different direction, they, for every frequency, was propagating with the same phase velocity. So the assumption was that below an array, here we see a circular array, for example, the waves that were recording were propagating with the same velocity, and below the array, the structure can be simply considered as a 1D structure. So he also assumed that the waves that were coming from different azimuth and with different, maybe even frequency contents, were statistically independent. So each one was generated by different source, activated in different time. So he was defining a spatial correlation just as a function of the distance between the two sensors. So for example, the sensor here in the center and the sensor here at the position X, which are at the distance R. Lambda is for a certain azimuth, but here it's called theta, but okay, we can call it lambda. So it was just the correlation of a signal recorded in this point with a signal that was recorded at another station. And this correlation, of course, is depending on the propagation of the waves between, let's say, this array of stations. And he was just calculating this for all the possible windows of signal. So if you then can make the azimuthal average of this function, so that you have now for one certain azimuth, but you do it for all the possible azimuth, and you just average on P, because this is the azimuthal average, you get a coefficient that is depending only on the distance. So this coefficient is telling how much the waves recorded at different stations coming from a different source are similar, okay, at a certain distance. And then also he tried to explain that this autocorrelation function depends on the power spectrum, and he showed that this function is a function of what is defined as a Bessel function. So this similarity as a function of distance was changing like it would change a Bessel function, which is a function a little bit similar to a cos function, depending on the frequency of the signal, depending on the distance, and depending on the velocity at which each frequency is propagating below the array. So in particular, what you can do, if you take stations in different position for different azimuth, but at similar distance, you just correlate the signal, you calculate the correlation coefficient, and for each frequency, if a signal is filtered at that frequency, you will have a coefficient of similarities. Then you take stations at larger frequency, you will have another coefficient, and so on. And this can be done for many frequencies in your signal. How this coefficient should change with distance? Okay, this should be like a Bessel function. A Bessel function having the same frequency, omega 0, having a certain, depending on the distance, and the value of this Bessel function will depend also on the phase velocity. So, of course, from the data, we can measure for the many stations that we have this coefficient for the different distances. And also, of course, we can do it for a certain number of samples of frequencies which are inside our signal. And then I can try to explain this variation of a coefficient as a function of distance as of frequency with a Bessel function. I know the frequency because I decide which frequency I analyze. I know the distance because I can measure the distance between the two stations. I only have to look for the phase velocity for that frequency that is able to reproduce a Bessel function that is fitting my data. So Aki had to do this, of course, in the time domain. So he had to filter the analog signal around a specific frequency. He had to calculate the maximum, the zero, and the minima of the Bessel function. And then he had to, in few points, calculate exactly which value was best fitting his observation. Nowadays, now we have many stations. We are collecting data with digital seismometers and calculating the Bessel the correlation can be very fast if, for example, we don't do it a frequency at each time, but we do it directly at all the frequencies using, for example, the Fourier transform. So what we are generally doing, very simply, for each of the recording, probably I have it here, okay, still in German, I have to change it. So for each of the recording, or every station, we calculate its Fourier transform. Again, we calculate the cross correlation between one recording and the other of every station. And we do it for many recordings. So we stack again, and this is my numerator. And we simply normalize this with a power spectrum, let's say, of the recording at the station J and the power spectrum of the recording at the station N. So in this way, we immediately have the coefficient, the correlation coefficient for all the frequency for each couple of stations. Okay? I just show you the an example, and sorry that it remains in German, but okay, I will explain it anyway. So we said that for a certain distance between two stations and for a frequency, the correlation coefficient should look similar to a Bessel function of 0 order. This is coming from the theory. So just imagine these are my recording of station 1. And these are my recording to the right of station 2. How I do my analysis? First, I divide all my signal in small windows from 1 to m at both stations. And this signal should be coincident. So the time when start of the window 1 at station 1 is the same time when the signal here is starting at station 2. So for each window, what I do? I calculate its Fourier spectrum. And then I calculate simply the cross spectrum like before. So for example, for the window number 3, I just multiply the Fourier spectrum of this window for the complex conjugate of the Fourier spectrum of this other window, always number 3, and so on. And then I repeat this for all the windows, and I just stack them. And this is my numerator, it's just the summation of this. Below in the denominator, I have nothing but the square of each window, which is summed for all the number of windows station 1, and here just the square of the Fourier spectrum of station 2 for each one of the window, which is summed. I just multiply the 2 and I divide for the number of windows. This is automatically giving to me the coefficient of similarities between the two stations, okay, for all my signal. And of course, I repeat this for all the possible combination of stations, because this is valid for one station, so for only one distance. Then I will do it for another distance if I consider another station, and so on. I can consider all the possible combination of stations of my array. Okay? So I would stop here for today, and then we see how to calculate the dispersion curve Friday. Do you have questions about this? Hello?
No. Yeah.
Ah, okay. It's all clear?
Yeah, somehow.
Somehow only?
Yeah.
Professor, I have one question.
Yes.
Can you show the slide where you were showing the velocity and frequency with maybe the dispersion?
Okay. You have to tell me which one, okay?
The one with LO.
This one?
Yeah.
Okay.
So the smaller frequency corresponds to high velocity?
The small frequency corresponds to high velocity, yes.
When the velocity is high, we have small time and the frequency will be high, no? I was just thinking, maybe I was following like...
No, I didn't get it. Why?
No, it just, I was thinking, maybe I was thinking in the wrong way. So what I was thinking was...
It's what I show you here, you see.
Mm-hmm.
Wait, I come to this point again, which is quite important intuitively. No, you see it here.
Yeah.
This is a high frequency,
yeah,
to the left.
Mm-hmm.
The wavelength is the velocity divided frequency.
Mm-hmm.
So you have a small wavelength. So generally high frequency penetrate not too much in the ground. So they propagate only in the slow velocity layers.
Yeah.
When you have small frequency,
mm-hmm.
you have long wavelength. Long wavelength, it means the perturbation is penetrating deeper in the Earth. So when it moves, just imagine this one moving in this way,
Yeah.
you see it's propagating the perturbation not only in the shallow layer, but also in the deeper layer that are generally faster, no?
Mhm.
And that's why then low frequency are faster than the high frequency. Okay, I'm talking about the fundamental mode, let's say, more or less. It's just an approximation, intuitive. It's clear? So if you go now here, you see exactly the same. Oops. The low frequency here,
Mhm.
they are faster because they are propagating, penetrating deeper in the Earth. The high frequency, they are only propagating in the shallow crustal layers, in the shallow superficial layers, let's say, where the velocity is low. And you see here, small velocity. Okay?
Yeah, okay. So
Is
now
it clear?
yeah, yeah.
Okay,
Yeah,
great.
thank you.
It's all clear?
Yes, for me now.
Okay, so if there are no other questions, then we can update on Friday from 9 to 10, okay?
Yes.
Great,
Okay.
very good.
Friday will be the last lesson,
Sorry?
or no? Venerdì è l'ultima lezione o no?
No. No. No, we still have Monday, Tuesday, and also
Okay.
the 22nd and 23rd. Exactly, I think it's the 23rd is the last one. So we have still 4 lectures, okay?
Okay, I guess that we received like a wrong, not the correct one, like the timetable was
Did
not
you
correct.
check on the web page of ICTP? They should be correct there. But if
There
you
are
see something different from what I have, send it to me. If maybe I have something wrong. Sometimes there are changes, but that's what I have on my agenda.
Ah, ok.
Chiara, if you see something different, please tell me, ok?
Avevo visto tutto un altro, infatti pensavo terminasse a dire però oggi, perciò non mi trovavo.
No. It's
Ah,
much
ok.
more. If you are not already, if you have enough, I can understand. But
No, no, perché aspettavo la lezione sull'early warning, allora a questo punto mi chiedevo quando...
Okay. This will come a bit later. Okay,
Ok, no, pensavo fossi saltata, perciò, grazie.
No, absolutely not. Okay, then see you all on
Venerdì.
Friday. Okay, ciao.
Ciao.
Bye.
Bye. Ciao.